Good afternoon, everyone. Today's topic is on urban air pollution, and there are several aspects I would like to talk about. So first of all is a little bit of history, cities through time, growing risks, global burden of disease, something about aerosol chemistry and concentrations, pollution dynamics, and then finishing off on the waves of innovation. Now, to start with this history, I will provide you with a little quote without telling you first where is it coming from. So this is that situation. Imagine that we are standing somewhere on the highest point here in Haifa, and let's see whether this description would apply to what we would see. A noisome brown haze would be hanging low over the city streets, capable of dulling the majestic polish and sparkle. Do you see situations like this here in Haifa, that there's that smoke covering the city? Or something which is, all right, so perhaps this is about here, perhaps it's another place somewhere in the world. Now, but when we read the second part of this quote, then we would start wondering that it is probably not Haifa or any other place in the developed world. Charcoal smoke from household kitchens, bakers' ovens, blacksmiths' furnaces, funeral pyres, and clouds of dust kicked by shuffling pedestrians. Well, this is definitely not Haifa, right? This is definitely not London or any other place like this. So where and when is this? It is Rome Anno Domini 66. So while we consider urban air pollution as a phenomenon of the current times, as per this quote, it's been with us for close to 2 millennia now, as documented by this reference. And further, if we look at the type of pollution sources present there, again, we could identify with the sources: brown haze, charcoal smoke, combustion, and dust in the air. Considering ancient Rome and its size, this was a city around the time when this quote comes from. The city was just over 1 million. At the time, there were two other cities of around this size, Alexandria and Antioch. So the pollution sources, as we can classify, were as such: combustion, charcoal smoke, city dust, dust kicked by pedestrians, photochemistry. This noisome brown haze implies that it was chemistry. Now, there's something else which was not implied in this little description, which is long-range transport, and particularly something which would have already been a source there being in this part of the world is the dust from Sahara. Has it been noticed then or in the ancient time that there was the dust and it was present? Now here we've got a little quote from an unlikely reference on air pollution from the Iliad. If we read this, I'm not going to read this whole passage and quote, but interesting when we see this rain, showers of bloody raindrops. So this was identified as the dust from Sahara. This actually was brought to my attention by a student, Greek student Eleni, a year ago or so, when we've discussed the history of air pollution. So air pollution and urban air pollution and the type of sources we had before have been present with us all through the history. Fast forward almost 2,000 years, not quite, but close, and we have a slightly different distribution of urban centers. So before we had that three: Rome, Antioch, and Alexandria. In 1800, we still have 3 cities over 1 million. But as you can see, powers have shifted, and it is these 3 cities which are now over 1 million. But nothing much has changed apart from this. Another step, much smaller step in the history, only 100 years, and now, as you can see, we already have 16 cities over 1 million. And what's changing? Something very important starts happening. Industrial revolution is starting. The next smaller step, 1950, only 50 years, and now we have already 74 cities with over 1 million. Industrial revolution is in full swing, and this is a photo of from London, infamous London smoke. In fact, this was the beginning of the shift in how air pollution was viewed. London was not the only place, it were the places, this cluster of places and sources here in the United States. Well, another step, 60 years, and we can see 442 cities, over 1 million, and in some places, particularly here when we look at it, it's like a continuum almost of this development. So we can conclude from this that this is growing population, and undoubtedly this is the case, and we have seen probably lots of graphs like this showing the population increase, and this what relate to what we said before, that slow progress and then very fast progress now and predictions for the future. But there is something else which we need to stress here. It's not just growing population, but the trend is urbanization. At this point already, we have over 50% of population, world population, residing in cities. And predictions for the next 30 years, it will be significantly more. If we look at this slightly different way of presenting this, so we have here the increase and here the years and prediction. So we can see that the green rural population will slightly decrease, but the whole increase of the population will be in the urban areas. So this is another aspect of urbanization, and the question is where this urbanization is occurring. And we can see this is the percentage, these are different areas, parts of the world, percentage contribution to the whole urban population of the world. And then we can see that Asia is the place where the population contribution to urban areas is and will be the highest. Now, another global problem, this is not global trend, but global problem, well, trend as well to mention, is energy increase. Again, this is something which is, we are quite familiar with, this is nothing new. I like this particular way of presenting this energy consumption because it is linked here over the time with the innovations and development. So what new innovations bring what energy consumption and what different sources of energy, so wood, which hasn't increased, and different sources of energy increasing. As we know very well, this leads to another problem, which is climate change. Again, there are many ways of presenting this. This is one from IPCC report. A color in red indicates that this is increase in the temperature, and we can see that basically the whole globe shows is in red temperature increase. And global problem, air pollution or urban air pollution increase. Now, I'm sure that we're all familiar and most commonly see this kind of images from China and hear about horrible air pollution there. But some of these images, this one, for example, here, it is not China, and I'm sure you can distinguish by the landmark what place it is. It is Paris in March last year. Now, this is Sydney, while Australia in general has much better air quality than many other places in the world, yet we see situations like this as well. So the problem is not really restricted to Asia. And this mix of air pollution is inhaled by people around the world. And the mix is toxic. It was a surprise to many organizations, and particularly government organizations, when this announcement came by the International Agency for Research on Cancer in 2013, classifying as carcinogen group 1 ambient air and ambient particulate matter, which means that we are all right now inhaling carcinogen number 1. Now, this was a little bit, when it was announced, was a little bit of a disbelief what it means, but that's what it is. So this brings us to air pollution and health, and we'll stay with this topic for a moment. The realization that air pollution is a problem that introduced to the air came around this time for the first time in 1950, this infamous London smoke. It's interesting, even a few years ago, when talking about this, we were saying that it was linked to about 4,000 deaths. But since then, there were lots of analysis and meta-analysis of the data, and now it is considered that there were about 12,000 deaths as a result of these 2 weeks of exposure, extreme concentrations, and at the time of inversion. One of the statements from one of the papers dealing with this, particularly stressing the role of particulate matter and the potential causal effect of particulate matter. Again, one large step to the current type of analysis conducted, and to this monumental study, which was global burden of disease. What is it? It quantifies causes of risk and health injuries and measured in DALI, which is disability adjusted life years, which accounts both for years lost due to death and years of life lived with disability. So if a child acquires illness due to whatever risk, and that then person lives for entire life with this disease, so obviously this DALI is higher. In 2010, 6 papers were published in Lancet. For the first time ever, Lancet published a special issue on one particular topic, on this topic of global burden of disease. Now, here are the 10 top risks as assessed from this study. 67 risk factors, 291 countries or diseases, 21 regions in the world. And this is the list of the 10 top factors. It's very interesting, while some of them are related to the lifestyle, but to see these air pollution related aspects at that very high places. Now this one, household air pollution, is particularly related to places when indoor air biomass burning occurs, like open fires. But this is ambient particulate matter. So these are particularly related to respiratory and cardiovascular diseases, cancer, and this ambient particulate matter means PM 2.5. So this is quite amazing how important, how significant it is. Now, how it is here in Israel? As you can see, the list of 10 top differs somewhat to the other list. There's no household pure pollution, implying, as expected, that there's no indoor biomass burning, but ambient particulate matter is even higher. Now, there could be different reasons to the reasons in many other countries or regions, because there is that dust from the desert, but whatever the sources are, it's quite significant that it is that high. Again, by comparison, we look at the Chinese risk factors, and here, interestingly enough, ambient particulate matter is number 4. That's how significant it is. Household air pollution still stays high, implying that there are lots of places in China and in many other places in Asia where indoor house, that open fire burning takes place. You may ask lots of questions how this assessment was done, because it's, as you can probably appreciate, how big task it is to compile all this information and to come up with this quantification. Of course, we won't have a lot of time to talk about this, but one specific aspect I wanted to mention is how this ambient particulate matter and its concentration was assessed on a global scale. Several ways of doing this. We are most familiar with ground-based particulate matter measurements, and there are stations, as I understand here in Israel, there are about 100 stations measuring particulate matter. But if you think about the distribution of pollution measurements in other places in the world, there are places where there are no measurements taking place at all. So therefore, we need to use other tools, and in particular, satellite measurements of the aerosol optical depths, then combining this and translating into PM2.5 together with predictions from global chemical transport models. And what comes from this are maps of this nature. So this is the estimated PM2.5 concentration worldwide, different concentrations. And interesting, when you see the highest concentration, there are in the places of the world, some of the places in the world, which are affected by desert dust. So we have this. What's the next step? The next step is to link this with exposure-response relation data. This is the graph from the WHO 2000 guideline, linking, in this case, it's PM10 with percentage change in several health endpoints. And what you can see here, that all these lines are, all these relationships are linear. Was it true? Well, there were question marks at the time, but particularly the question mark around this area, because it was extrapolated down to these lower values. And also, as you can see, this stopped here around 200 micrograms. So this was 2000. Since then, there have been significantly more studies, experimental and modeling, showing the picture, not necessarily slightly different, extending the picture to other sizes, to other concentration levels. So from this particular study, I've selected these two, ischemic heart disease and acute lower respiratory infection in infants. So we've got concentrations of PM2.5 and the response. Now, how these two curves, these graphs compare to this, we can see still the linear parts in these sizes, which correspond to what was considered linear before. But the studies went significantly to lower concentrations in both cases, but also to upper concentration. Important aspect here is that in the upper concentration, there is that leveling, which has very, very significant impact on management, and it's kind of a pain for the governments. It means that lowering, controlling pollutants from this concentration to this concentration will not have any effect on health. It would require much, much significantly more. Speaking about the lower concentration, it's still the question, is there a threshold? And it doesn't seem that there is a threshold. If anything, it goes here to very low concentrations, but these are basically background concentration. So for any concentration we can measure, there are always health effects. So we could, in a way, summarize this particular aspect as a global trend. Ambient particles among the top risks through the history, from outdoor and indoor sources, we'll talk about indoor sources on Sunday, and affecting increasing number of people. So let's talk a little bit about the concentrations. Unfortunately, we cannot compare the concentrations with those in ancient Rome. No monitoring was conducted then, nor at the beginning of the Industrial Revolution. But there are already data from the 50s from London. We've got the maximum smoke concentration, which is basically TSP, and you can see how huge values levels measured in milligrams. Well, normal concentration was also very, very high. This is just curiosity to show also surface SO2, and that's how graphs in scientific papers looked at that time. Fast forward, of course, things change, and this was that in the 50s that London smoke and smoke in Donora in Pennsylvania was the change, and Clean Air Acts were introduced, the first one in the United States in 1952. And if you go to London now, the concentrations are much, much lower, and you can see signs like this. I'm not sure whether you can read this, but it says air quality management area, and urging drivers to turn off engines if they are waiting or so on. So there has been a significant change. If we look at the concentrations or the distribution of concentrations across Europe, this is, I selected this as one interesting diagram. So we've got different countries here. We won't talk about the individual countries or cities. In different colors, we've got the areas: remote, rural, urban, industrial sites, and this is for PM10. So we've got average, median. So what we can see, just looking from a very general perspective of this, that the concentrations are in general below 50 micrograms. We can also see that there is an increase in concentration between remote sites and the urban curbside. We can also see that there's the concentrations are higher in Southern Europe, whether it is because of the contribution from the dust from Sahara. It's certainly an important factor on this, and I see lots of papers on this. So this gives a perspective of the current concentration, which are significantly lower than the concentrations in London in the 50s. We can look at this data in many different ways, trying to apportion the pollution. This is one of them, linking PM2.5 and PM10 for various types of aerosols. So if we put them together on one graph, we can, in a way, apportion what's coming from road traffic, what's coming from dust. This is obviously one way of doing this. We had discussions yesterday, what are the contributions here to what's in the air, and it's a very important question, as you can imagine, for management. But if we look at the situation in China, the picture is a bit different. Here there are a few cities from which data for this period 2007-2008 were measured. And as we can see, the concentrations are much higher. Xi'an is the highest, going to 100 something. Any questions? I'm happy to take any questions or comments.
We just have a new campus in Guangzhou, so...
Okay, so you are content.
We cancelled the flight.
Okay, well...
We will rebook it.
Well, I hope that the next image wouldn't discourage you again, because we see often reports like this. So this is a particular event, and you can see that PM2.5 going to 1,000 micrograms per cubic meter. So the concentrations are enormous. One aspect which is not covered by this kind of measurements, PM2.5, is the ultrafine particles. There are some papers compiling the data, but they don't present such a nice picture. So what I did here, I would like to show a slightly different way of presenting ultrafine particles. Now, particle number concentration or ultrafine particles, we can talk in a different ways about this, but basically we are talking about the particles which are in general smaller than 100 nanometers. Compiling data from various publications, we can see as expected, the increasing trend from rural to background, urban, and so on to tunnels. And we can see that there's a pretty good agreement between studies conducted in different parts of the world. But there's something important to notice here, comparing this graph with the graph which I showed a moment ago for PM2.5 concentration across Europe for different sites. While there, the vertical scale was linear, here vertical scale is logarithmic. So this shows that the increase near the sources, which are vehicle emissions, is logarithmic. Ultrafine particles, particle number, is the best indication of combustion, vehicle combustion. Why? Because, like from any combustion, the majority of the particles in terms of number is emitted in the small size range. So we've got a few size distribution, size spectra here. Compressed natural gas, we can see that the peak is 12, 14 or something like this nanometers. Petrol is slightly bigger, around 40 nanometers. Diesel, dependently what's the composition, has 2 peaks, but still it is, the majority is below 100 nanometers. And as a result of this, what's in the air, in the ambient air, the majority in terms of number is in the ultrafine size range, again, logarithmic scale here. One other aspect important to point out is whether measurements of PM2.5 give us any information on particle number. Now, what we have here is the last slide in the corner from the previous graph, but now this is linear scale. Sometimes linear scale allows us to see some features better. So this is the majority of the particles in this ultrafine region. Now, let's assume that the particles are spherical and then, that we know particle density. So let's recalculate this into particle mass. And the diagram looks like this. Where we couldn't see any particles by number, that's where the whole mass is. Where there's basically nothing in terms of mass, this is where all the number is. So really, these measurements by mass, and here these are the boundary of what PM2.5, PM10 measures, they don't provide us with basically any information on particle number, which is the best indication of traffic emissions in the city. So one kind of curiosity here, which relates to what we've discussed, but also relates to various other types of environment. We don't have in Australia dust storms, and if it happens, it's once in a blue moon. In all my time in Australia, it happened only once. That's how Brisbane looked like at the time. And interestingly enough, this dust came from Lake Erie, which is in the center of Australia. It's an interesting phenomenon. After it's normally dry, after rains, it's filled up with water, then it dries again. And then this very fresh dust is resuspended by wind, if it happens to be a very strong wind event, and it carried this dust all across Australia to Sydney, to Brisbane, more than 2,000 kilometers. Now, what's happening here is we were not prepared for this measurement. It's just an opportunistic measurement. We were in the middle of measuring something else. So we've got here time. So this is that plume arrived to Brisbane around 11 o'clock or something like this in the morning. And these are the concentrations, separately concentrations for PM10 and secondly concentrations for particle number. Now, before it arrived, we can see that the concentration of particle number is typical for Brisbane, about 5,000 per cubic centimeter, and typical a few micrograms per cubic meter for PM10. Now, what we can see immediately when the plume arrived, well, concentration mass is shooting up, but concentration of particle number is decreasing. Why? well, these particles now find such a huge thing in terms of surface area of these larger particles. You can, and that's what we did eventually, we did calculate some elements of dynamics. You had to be in situations like this very careful with the media. What was the media take on this graph? The dust storm cleaned air from ultrafine particles. Well, we had to then make sure that they wouldn't put this in the press as such. So what we can conclude from all of this as another trend. So in this sort of first level, we can say in the Western countries like London, there's a decrease in particle mass. In Asia, there's increase in particle mass. But there's more to it. And particularly, we don't see even the management of emissions progresses. We don't really see this trend. There's the decreasing trend. If anything is increasing, the next GBD for Australia is showing from what we've calculated 0.5 microgram increase. There's another aspect of this. What is the trend for particle number concentration? And the question is, because of the surface area, is it opposite? So it means that the concentrations are increasing. Well, so far I've been talking about physical characteristics, but there's also the whole world of chemistry which can be investigated in many different ways. As you can see, these chemical components in different cities. I have natural tendency to talk about physical aspects, being physicist, but sometimes the real-time measurements by the instruments we have for physical parameters give us a more detailed picture than the picture it's obtained from chemistry. But there's one aspect which I wanted to show you, one of the many examples, and this is an example of the variation in the composition dependently on the source, and particularly with the changing of the sources. This is one of the experiments which we've conducted, and what we've got here, we've got emissions from a diesel vehicle and a CNG vehicle without thermodenuder and with thermodenuder. So basically, we took the emission and we heated the particles to about 300 degrees. Just please ignore this, that Z ratio, but just treat this as concentration. This was part of a bigger study. Now, what we can see that after heating these particles, the diesel particles didn't, well, there was a change, and here we are talking about concentration of the diesel particles. There was a change, but this change was not as dramatic as the change in CNG particles. What is this implying, or what we can conclude from here? That basically this particle, a large fraction of these particles are volatile. So this is now a completely different, with this kind of sources, there's a completely different picture of what is emitted from combustion to the air. So we've got the sources, local combustion, vehicle exhaust, but others as well. Non-exhaust emissions, like any bits and pieces of tires, dust were suspended, secondary formation processes, and long-distance transport. Now, I don't think I need to convince anybody that in most urban environments, vehicle emissions are the most obvious and the most important source. Operation of this source then is related to emissions. So this is a typical camel curve, which can be seen, I would imagine, in any city. Time 24 hours, hourly mean traffic. So there's one hump of the camel in the morning and the second hump of the camel in the afternoon, and a little bit between this. Therefore, there's not surprising that we see this similar type of response in the concentrations. These are concentrations measured by the air quality stations of the network operated by the Queensland government. And we can see for the stations again, for all the stations, the same shape. There is a variation, but again, the variation between the concentrations is a factor of 30%, 50%, not much more than this. But in this case, the concentrations, as we expect, follow operation of the source. We also have a similar picture when we measure particle number concentration. So we've got traffic, it's in red, and in blue concentration, or the other way around. But in any case, the hums of traffic and the hums of concentration, particle number, follow each other. I'll show you in a moment a very different picture to this, but before this, the issue of non-exhaust emissions. This is a topic which is coming, and there's not still a lot information or very good quantitative information. But the current assessment is that in the years to come, and in very soon, this will be the most significant contribution to settling particle mass. So it's expected to be the dominant component of vehicle emissions related to vehicle emissions. And according to this assessment, already by 2020, the contribution will reach about 90%. Certainly it depends where, but this is the way things are going. Primary versus secondary particles, that's what I or we find most interesting. So the primary particles are those which are emitted directly from the sources like this soot from the vehicles, and secondary particles which are formed in the air from the gaseous or vapor precursors. They don't necessarily follow this dynamic attracted to each other. The process is a bit different, but that's the end. This is the end product. And now the whole world is basically following, tracing, chasing the so-called banana curves. So formation of secondary organic aerosol, and this is an example. So very rapid increase in concentrations when the conditions are right for formation of these particles, followed by the particle growth, and therefore there's this shape of the banana curve. So we have two bananas in this graph. If you go nowadays to aerosol conferences, I'm sure David can support this statement, a significant part, maybe even half, but significant part is devoted to various aspects of this complex processes. What in general terms have been conducted from the studies mainly conducted on the northern hemisphere? Our studies in Brisbane are among the only ones so far conducted in the southern hemisphere, that there is a rapid increase in particle number concentration by 2 to 3 orders of magnitude, and then followed by particle growth, which is the banana. Two types of these nucleation events were identified, two main times. There are some other perhaps less significant. Morning rush hour increased, so that's particular when the temperature is low, and this midday formation, and here the photochemistry and increased solar radiation in the middle of the day is the most important factor. So now back to the very similar diagram which we've seen a moment ago. So this is traffic that our camel humps, and this is particle number concentration. What basically disappeared, or it's not seen in this scale, are the morning and afternoon peaks, because they are significantly overshadowed by that SOA peak in the middle of the day. And I must say that this is something which used to be exotic to us at the beginning when we started these measurements. We read about this, but we've never seen it in Brisbane. But now it occurs in Brisbane every second day, every third day. Something has changed in the whole dynamics which is causing this to occur. Now, just one example of something like this occurring also in Hong Kong. And this is an example because in other Asian cities, researchers also identified this to occur. It is interesting because there's such a large mass of the larger particles, so one would expect that it doesn't occur there, that instead the vapors condense on the surface of the larger particles. Yet there's been lots of observations of secondary particle formation in Asia as well. So as a result of this, what we are concluding is that as a result of urban vehicle emissions and SOA, Up to 90% of particles in terms of number is in the ultrafine size range, and even big fraction of this is even smaller in the range of below 50 nanometers. Now, one aspect, I'm not going to talk in any quantitative way here, is long-range transport. These are just pictures from my observation, like this one in Seoul or in Hong Kong. The situation here was, I was there for a few days, crystal clear air, very good view, and one morning I'm waking up and Seoul looks like this. So I asked my colleagues, what has changed? What's the reason? And what was the answer? Wind direction changed, and wind was blowing now from the west, bringing air masses from China. Or in Hong Kong, similar situation, bringing air from the continent. Well, we've already talked about this long-range transport. This is not a photo which I took, quite dramatic, from the, I think it was in Iran. But I'm sure you know much more on this topic than I, because you are impacted by this. So the general type of trends we can conclude is that there are expansion of source types, adding complexity to basically everything, to atmospheric chemistry, atmospheric dynamics, source apportionment, and pollution management and control. I would like to finish with something different, because we are all knowing, yes, this is the case, what we've seen here, we know all about this. We can discuss some quantitative aspects of this, but is there awareness about air pollution among the greatest community? This is a photo from that particular place, popular place in Brisbane. It's kind of in the middle. We don't have very high risers in this part on the other side of the city. And this is a very popular Greek restaurant here, and with lots of tables. I don't know whether you clearly can see of Peterson. So it is, as you can see, surrounded by this traffic here. Are we aware, and I'm not talking even of people somewhere there who know nothing about air pollution, are we here aware that this is a problem? Would we choose to sit outside here because it's cool rather than sitting inside? Will we bring candles to our dinners to make ambience and so on? And if we can continue like this, the problem is that in the general community, there's basically no awareness of air quality unless the situation is such that you can't see at this rate. So this is a big, big problem. We have now a project in which we will investigate it, explore the ways of providing people with information of their mobile phones. So say that people would be able to receive this kind of alert. You have just reached 75% of the WHO recommended maximum daily exposure limit. Do we care about this, or do people care about this? So technology is progressing fast. This is already basically possible. It will, we hope to finish the project in 3 years' time. It will be possible. But the awareness and teaching different behaviors, this is far, far behind. So role of social science and working with social scientists. Finish off the waves of economic change. It is interesting to see the time and innovation. There's no scale, but basically each of the innovations, each of the discovery or development brought new innovations. And you can start from iron, from different sources and so on. So each of the waves brought higher number of innovations. We are now in this green economy innovation. And here the sky really is the limit in terms of what these innovations can and will do in a not too distant future. Toda.